8C gas laws. 8 November, history of the gas laws. Scientists began experimenting with gases almost as soon as Galileo demonstrated the value of scientific observation. His secretary, Evangelista Torricelli, invented a barometer in 1643. Earlier, Gasparo Berti proved that gases have weight. Shortly after, Robert Boyle investigated the springiness of air. In 1702, the French scientist Guillaume Amontons built a thermometer that worked on the principle that the pressure of an isolated quantity of gas was proportional to its temperature. Using his thermometer, he was the first to make an approximation of absolute zero. In 1787, Jacques Charles, another French scientist, built and flew in the first hydrogen balloon. His research revealed the relationship between the temperature and the volume of an isolated quantity of gas. In the last decades of the 1700s, much evidence was accumulating to discredit the Aristotelian theory of continuous matter. John Dalton, who is best remembered for his atomic theory, set the stage for that revolutionary theory when he observed in 1801 that atmospheric pressure is just the sum of the partial pressures of individual atmospheric gases. In other words, each gas exerts its own pressure as if it were the only gas present. The partial pressure of each gas depends only on its temperature and the density and molecular mass of its particles. In 1708, Joseph Gay-Lussac discovered through a series of experiments that when gases chemically react at a constant pressure and temperature, their volumes combine in ratios of small whole numbers. For example, 2 volumes of hydrogen combine with 1 volume of oxygen to produce 1 volume of water vapor under the same conditions. This discovery offered significant support of Dalton's atomic theory. Just 3 years later, Amedeo Avogadro explained Gay-Lussac's results by showing that equal volumes of gas contain equal numbers of particles if they are at the same temperature and pressure. These breakthroughs contributed to the acceptance of the particle theory of matter. As you can see, scientists made great progress in understanding fluids, especially gases, in the 18th and 19th centuries. The rest of Section C discusses 2 of the most important gas laws, Boyle's law and Charles's law. Boyle's law. You can properly understand gas pressure only by understanding what occurs at the particle level. At room temperature, a single gas molecule speeds along at about 1,000 meters per second. It has momentum because of its speed and mass, P equals mxv. When it collides with a solid surface, it exerts a force on the surface and rebounds in an elastic collision. The force of this collision is minuscule for a single molecule, but with many trillions of molecules colliding with a surface, this force is multiplied trillions of times per second, resulting in a measurable pressure. Gas pressure depends on the number of molecules present in a volume of gas, their masses, and how fast they are moving. The average speed of all gas molecules in a sample of gas determines the temperature of the gas. The faster the gas molecules move, the higher the temperature. A gas enclosed in a container has a fixed number of molecules in its volume. The average number of collisions per second of gas molecules with each other, and the container's surfaces is constant for a constant temperature. What would happen to gas pressure if the container's size were reduced without changing the number of gas molecules or their temperature? Reducing the container's size decreases its volume and the distance between molecules. Thus, the number of collisions per second increases because the molecules have less distance to travel between collisions. Keeping temperature constant means that the molecule's average speed is constant. Therefore, the average molecular momentum, and thus the average force per collision, is constant. Combining these factors, you can see that the total pressure on the container's walls will increase as its volume decreases. If the container's volume is enlarged, gas pressure decreases because molecules must travel farther between collisions, reducing the rate of molecule collisions. Robert Boyle discovered this relationship between volume and pressure in experiments during 1659 and 1660. He trapped a small amount of air in the sealed short end of a glass J-tube by pouring liquid mercury into the open long end. When he added more mercury, the volume of trapped air decreased as the height and weight of the mercury column increased. He discovered that the volume of the trapped air was inversely proportional to the pressure exerted by the mercury. In other words, if he doubled the pressure on the gas, its volume decreased by half. He found this relationship to be true for any volume or pressure of air, as long as he measured a fixed amount of air at a constant temperature. The inverse relationship between the volume and pressure of a confined gas is called Boyle's law. This law can be expressed by the formula P equals K over V, or equivalently, PXV equals K, where P is the pressure of the gas, in pressure units such as newtons, per square meter or pascals. V is the volume of the confined gas, in volume units such as cubic meters. And K is a constant, its value is not important. For a fixed amount of gas confined at a constant temperature, the product of any pressure and its corresponding volume will equal the same constant. P1xV1 equals K, and K equals P2xV2. Since K equals K, we can substitute the two products of PV for K. P1xV1 equals P2xV2, which is the standard formula for Boyle's law. The quantities with the subscript 1 are the pressure and volume at one set of conditions. The subscript 2 indicates the pressure and volume of the same amount of gas at another set of conditions. If you know any three of these quantities, you can calculate the fourth using simple algebra. What are some practical applications of Boyle's law? People use compressed air for all kinds of purposes, such as filling sports balls, operating powerful shop tools, and even painting with airbrushes. Manufacturers of compressed air tanks know that a small tank containing the same amount of air as a larger tank has a greater pressure exerted on its walls. Such considerations are crucial. If the smaller tank were not constructed with thicker walls, it could explode. Boyle's law also explains why meteorologists only partially fill their high-altitude balloons with helium before they release them. As the balloon rises into the atmosphere, the surrounding air pressure decreases, and the volume of the lifting gas increases to fill the balloon. If the balloon were full when released, it would burst before reaching the desired altitude. 8.13 Charles's Law. Tightly cover a glass bowl with a sheet of polyethylene food wrap and place the bowl in a microwave oven. After heating the sealed bowl for a short time, you'll notice that the food wrap has bulged upward like an inflated balloon. What has happened, and how can we explain it? The food wrap traps a fixed amount of air in the bowl. When microwave energy is added to the trapped air, its molecules vibrate faster and gain kinetic energy. When they collide with the food wrap and the sides of the bowl, they exert a greater force with each collision, and there are more collisions per second. Both of these effects increase the pressure of the trapped air. The elastic food wrap stretches because of the trapped air's higher pressure. The force exerted by the warmed food wrap on the trapped air is negligible and can be ignored for this illustration. It merely forms a boundary between the hot trapped air and the cooler outside air. The trapped air expands because its pressure exceeds the outside air pressure exerted on the food wrap. An equilibrium occurs only when the microwave is turned off and stops heating the air. All forces on the food wrap are balanced, Newton's first law. Though the trapped air particles are moving at higher speeds, they are now spread out because of thermal expansion. Thus, the rate of molecule collisions drops. The net effect is a lowering of inside air pressure, so that it equals outside air pressure. The original amount of air now occupies a larger volume at a higher temperature. We can observe from this demonstration that, for gases, a direct relationship exists between volume and temperature. For a given quantity of pure gas, as temperature increases, its volume increases if pressure is held constant. This principle is known as Charles's law, in honor of Jacques Charles, a prominent 18th century scientist, known for his exploits as a balloonist. Charles's law says that the volume of a fixed amount of gas changes in the same way as its absolute temperature, at constant pressure. This relationship can be expressed in the formula V equals K times T, where V is the volume of the gas in a volumetric unit such as liters. K is a proportionality constant. Its value is not important. And 'tis the absolute temperature of the gas in kelvins. The formula for Charles's law can be rearranged to isolate the constant factor on one side of the equation, just as with Boyle's law. The gas sample's volume and temperature at different conditions can be predicted because their ratio always equals the same constant. V1 over T1 equals K, and K equals V2 over T2. Since K equals K, we can say V1 over T1 equals V2 over T2, which is the standard formula for Charles's law. As with Boyle's law, if you know any three of the quantities, you can easily solve for the fourth. Remember that this relationship holds only for a fixed amount of a gas at constant pressure. Also remember that the absolute temperature, in kelvins, must be used as the unit for temperature. Gas molecule kinetic energy decreases continuously as temperature decreases toward absolute zero. The only temperature scale that can correctly relate properties that depend on particle energies is the Kelvin temperature scale.